canonical quantum gravity is worth studying and trying to point out at least two major philosophically interesting and substantive questions that arise in the context of canonical quantum gravity. So if you're an expert on canonical quantum gravity, as some of you are, then you may as well pull up your email at this point or go for a walk and not, in any way insulted if you do that, because you will learn absolutely nothing in the next 60 minutes. So that's one talk, one remark. The other one is that...
they learn what philosophers might find interesting?
Yes, I mean, yes, if you're a physicist working in canonical gravity, maybe you're going to learn what philosophers might find interesting in there. That's true, but you probably know that already anyway, because otherwise you wouldn't be here. The other remark is that I have way too many slides for 60 minutes. Really, this should be a 90 minutes talk. It's not, alas, so that means I will skip some of the slides. They're still there. I decided not to delete them, so that when you go to the website, beyondspacetime.net, you will find the full slides, and you can, go over some of that in case you're interested. Okay, good. Let's go then. We also added, Nick convinced me to change just that title to make it, clear that we don't expect philosophers of religion and ethicists and people like that to follow what I'm going to say easily. So I don't really presuppose much, but I presuppose a little bit of familiarity with physical theories and with, the way you do that. Okay. Now, there's two major problems I'm going to discuss and I'm going to focus on. One of them will be the notorious problem of time that arises quite generically in canonical quantum gravity, and as a matter of fact, of course, already at the classical level. And so I'm going to spend the first half talking almost exclusively about the classical cooking up of general relativity so as to make it amenable to a treatment in canonical quantum gravity, which is what leads to the problem already. Many of you are familiar with that, but I'm trying to show how exactly it arises and maybe some of the reactions, not just from physicists as we've seen them in the previous talks, but some reactions from philosophy, of which I think there are way too few. The second problem I'm going to talk about is the fact that not just time or change in a way disappears from fundamental physics, but space-time altogether. That is, the spatial geometry as well is going to look very different. As a matter of fact, there's a sense in which there is no space with the geometry in the usual way that we think about it, at least in one prominent approach to canonical quantum gravity, even though we will probably expect something similar to happen in other approaches into canonical quantum gravity as well. And that dissolution of space or space-time in loop quantum gravity will be so I have my 3 slides about loop quantum gravity as well, and then I'm trying to show how, not with specific physical work in physics that you can solve the problem, but more sort of generally how you should think of trying to recapture or regain space-time from the fundamental structure. Okay, so on with quantum gravity. The vantage point, of course, is classical general relativity, and the strategy that is employed in this family of approaches is to apply a canonical quantization procedure, which has earned its keep in other quantizations when we quantized other classical fields quite successfully using that recipe. So the hope is to use roughly that procedure in general relativity to get at the quantum theory of gravity. As every other approach, this approach claims to be conservative in that it tries to use what's known and established as good physics and as principles in a theory of gravity that work and that are central lessons of both GR and the quantization procedure that is successful on other occasions, and with the most minimal possible changes or innovations, try to get at the quantum theory of gravity. There's, of course, several families of theories in this very broad, encompassing tent of approaches, and loop quantum gravity is just one of them. And even loop quantum gravity, as is worthwhile to point out, in a way, is kind of a family of theories, or there's a number of different ways to think about loop quantum gravity and to extend it so that, strictly speaking, it's not loop quantum gravity anymore. Okay, what I'm going to say, large parts of it is really covered in these two papers. One I co-wrote with Nick and Tiziana, and is already published, and another paper that I wrote for a collection edited by Dennis Lemkool. I think both of these papers should be available from my website. Okay, good. Now, why canonical quantum gravity? I'm going to be extremely brief here. John Ehrman has argued that a canonical formulation of general relativity is desirable or has certain advantages. It explains how the fiber bundle formalism arises in cases it does. It has a sufficiently broad scope to relate GR to Yang-Mills theories. It offers a formalization of the gauge concept. It connects to foundational issues such as the nature of observables and the status of determinism of GR and gauge theories, and so on and so forth. And I think he has a couple more. But, there's a natural affinity to the initial value problem in standard GR as well. But the most important advantage for our purposes here is that it makes GR amenable to a canonical quantization procedure. That's the single most important advantage. There are, of course, also some disadvantages, as pointed out in particular by Tim Maudlin in a paper directly responding to John Ehrman of about 10 years ago, called Thoroughly Muddled MacTaggart, or How to Abuse Gauge Freedom to Generate Metaphysical Monstrosities. I will talk more about the metaphysical monstrosities that are supposed to arise in this context. But for now, for Maudlin, to recast GR in Hamiltonian as a Hamiltonian system is to force it into the Procrustean bed. I don't know whether you know how well versed you are in Greek mythology, but I think Procrustes was a bandit who would attack travelers and force them to or force them to sleep in a bed which they wouldn't fit them, which would be too short, and if they didn't fit, he would cut off, I think, their feet, so to make them fit into that bed. So in a way, applying Hamiltonian formalism to GR is like cutting off an essential part of what GR is supposed to be about, as far as Maudlin is concerned. And the problem really is that in many ways, a Hamiltonian system, or a Hamiltonian formalism, is very, very adequate when we talk about physical systems that are spatially extended and that evolve somehow over time. Now you might say, well, what about spin degrees of freedom? They're not really spatially extended, they're like internal degrees of freedom. That's true, you can have point particles with internal degrees of freedom that are amenable to a Hamiltonian treatment, but nevertheless, these are systems, points that are supposed to be in physical space that evolve over some physical time, something like that. And of course, that means you have to recast the four-dimensional space-time now somehow as three-dimensional spaces which evolve over some fiducial, some sort of privileged, physically privileged external time according to some dynamics governed by something that looks like Hamilton's equation. And of course that seems to violate the one of the most central dictums of modern physics, namely that what Minkowski has joined together, no man should put asunder. So we have a four-dimensional structure, and there's a reason why this is the best mathematical treatment. Of course, this is the natural way to encode Lorentz invariance, and that seems to be flying in the face of this. Anyway, let me say a little bit in more detail how how this Hamiltonian GR is now done. So one way to do it is to start out from a Lagrangian formulation, which, of course, in many physically relevant systems, we are both amenable to a Lagrangian and a Hamiltonian treatment, even though that is not the case by necessity somehow, by metaphysical necessity. These two could come apart, and in some cases, of course, they do. So let's start out from an action called the Einstein-Hilbert action for gravity without matter. Now that's important. There's some important restrictions or limitations of that approach, and one is that it has turned out to be much easier if you just look at the vacuum sector, as it were, of GR, if you don't include matter. And secondly, as I think I say it somewhere on the slides, but if not, let me emphasize that as well. GR is a famously promiscuous or permissive, perhaps I should say, permissive theory, in that it allows all sorts of crazy causal structures in spacetimes and wild topologies, really, because it makes very stringent, it puts up very stringent conditions on the local physics, but globally, it's actually it's probably way too permissive in many ways. And this treatment is, of course, only going to work in those cases where the topology is such that you have a three-dimensional topology times R, so that you can, in fact, dissect the four-dimensional structure into a 3+1 dimensional one. And that's not in general true in general relativistic spacetimes, of course. Anyway, if we have an action like that, we can get a Lagrangian formulation with Euler-Lagrange equations, which replace the vacuum Einstein equations if we vary the equation 1 with respect to the metric. If we do that, we find that the equations are second order, where the solutions will be uniquely determined by the generalized position and velocity variables in the Lagrangian approach, just in case the so-called Hessian matrix, this thing, do you see this well enough, including the indices, even in the back? Okay. So this matrix, which is an n by n matrix, where n labels the degrees of freedom, if that matrix is regular, it's not singular and therefore invertible, only in those cases will Q and Q dot uniquely determine the solutions of these second order equations. If not, then the accelerations Q double dot are not uniquely determined and the solutions will contain arbitrary functions of time. So the impossibility of inverting that matrix, of the singularity of that matrix, points to gauge freedom. Okay, good. Now that's the Lagrangian picture. Let's move on to Hamiltonian picture now based on that, or start using the Lagrangian as a vantage point. We can of course introduce canonical momenta now using this well-known way to do that. And transpose these Euler-Lagrange equations, dynamical equations, into Hamiltonian equations of motion, which have this well-known form here. N, of course, is again the number of degrees of freedom. Now, again, these canonical momenta, Pn, are not going to be independent from one another in case the Hessian matrix shown on the previous slide is singular, meaning that we will have, again, a case of gauge freedom. And these dependencies can be articulated or expressed in so-called primary constraint equations, where m is the number of dependencies. It's going to be smaller than n, of course. Okay, good. So we have these constraint equations. This is some function of the phase space variables, of the canonical variables, equals 0. So that's a constraint on them. Good. Now, of course, that will define a submanifold in the phase space where these equations are satisfied, the so-called constraint surface. Good. Now, here, as elsewhere, I cut a number of mathematical corners, as it were. Things are a bit more rich, really, when you look at the full mathematical articulation of what's going on here, and I just don't have time to go into everything, so I try to hit the highlights and make you, if you don't already know all of this, make you, eager to go and explore it by yourself. Okay, good. So the Euler-Lagrange equations turn out to be equivalent to the union of Hamilton's equations and the constraint equation, and we get an equation of motion for arbitrary functions of the phase space variables in the usual way, except that we have this additional term where these are the extra variables that we need to render the Legendre transformation between the canonical and sort of the Hamiltonian to Lagrangian invertible. And these arbitrary functions in 4 entail that the physical state is uniquely determined by a pair of canonical variables, but not vice versa. So a point in phase space determines the physical space, but not the other way around. So in that sense, we have again the codification of gauge freedom in that picture. So these UMs are encoding that. And again, this means cutting some mathematical corners. That's a technical expression. We get the physical phase space defined as the set of points representing gauge equivalence classes of points in the phase space, where these gauge equivalence classes are now non-trivial in the sense that they don't just contain one point. Okay, so that's the sort of the mathematical basis for now the philosophical problem that's going to follow. And some people, John Ehrman and Gordon Bellot, have called this Parmenides' revenge. I don't know, are you familiar with ancient Greek philosophy? You know about Parmenides? So Parmenides was the one who argued against Heraclitus, saying that there is no change. Fundamentally, there's only one unchanging, uncorruptible thing out there. And, whatever change we perceive in the world is somehow, arises in some sense as an illusion out of this fundamentally non-changing world. Okay, and Heraclitus says, but that's crazy. Change, if anything, is the most fundamental aspect of reality. Everything's changing all the time. Anyway, that was the ancient debate. And at the time, most people thought that Heraclitus really had the better arguments, that Parmenides is kind of like, obviously, not empirically adequate in a very straightforward way, right? If you essentially say everything we perceive is just an illusion. Now, some people have argued, Ehrman and Bellot, for instance, that what's happening here in Hamiltonian GR is his late revenge, because, as it turns out, fundamentally things really are not changing. This is what this is going to suggest. Because if we now understand GR as a constrained Hamiltonian system, then it turns out that the Hamiltonian function itself is a constraint that's bound to vanish on the constrained surface, and this is what will lead to the problem of time. Bianca said she didn't like that expression. I don't know her reasons for that. I don't like it either, and my reasons are that I think at least this formulation of the problem should be more appropriately called a problem of change, not necessarily time, because it says there's no change. Whether it says there's no time as well is a sort of an additional question, it seems to me. Anyway, now, before we get there, there's a crucial assumption that we need to make in order to get to the problem of change here, and maybe this is what Bianca referred to as naively one gets this problem. And one gets this problem if one thinks about Hamiltonian GR in the way one usually and standardly thinks about gauge theories quite generally. Namely, that only the gauge invariant quantities are those quantities which capture the genuine physical content of a theory, So that two distinct mathematical models of a theory may describe the same physical situation just in case they're related, or do describe the same physical situation just in case they're related by maps which are interpreted as so-called gauge transformations. So that's the sort of the standard way of thinking about gauge. And if that's standard, that's a crucial assumption now that the problem arises. And it has to do with the concept of Dirac observables, which are the technical concepts that, or the technical notions that encode the gauge invariant quantities, again, on at least somewhat naive, straightforward way of thinking about what's happening here. I think Brian is going to tell us that this picture is not quite right, but I'll leave it to him to do that. Anyway. So here's how we get to the problem. I need to introduce a couple of definitions here. Function, any function of the canonical variables is termed first class, just in case, and this shows that we're still at the classical level, the Poisson bracket with every primary and secondary, whatever these exactly are, constraints vanishes weakly. That means it vanishes on the constrained surface. That's what this is supposed to mean. That's what weakly vanishing means. And if that function f is itself a constraint, we call it a first-class constraint. That's just a bunch of terminology. Now, an equivalence class, or a Dirac observable, is defined as the function or the set of functions in phase space that have or has weakly vanishing Poisson brackets with all first-class constraints. And equivalently, we can therefore say the Dirac observables are the functions in phase space which are constant along gauge orbits in the constrained surface, and in that sense capture the gauge invariant quantities. Now, if all of this is the right way of thinking about the Hamiltonian general relativistic theory, and in particular, if the gauge invariant quantities of a constrained Hamiltonian theory really are the Dirac observables as I just defined them, then the physical content of the constrained Hamiltonian theory is exhausted by the Dirac observables. So all the really physically fundamental, genuine stuff along this way of thinking about the theory anyway is captured by the Dirac observables. And of course that means we have to go and identify the first-class constraints so that we can actually get a handle on what the Dirac constraints are. Okay. When did I start actually?
About 25,000.
Oh, okay. Okay. Well, GR, general covariance, there's a lot of subtlety here. I could spend the rest of the day talking about what general covariance really is and how we should think about it. But very roughly, and at least the way many physicists in canonical quantum gravity think about it, it just means that the Einstein equations have a dynamical symmetry group, the active four-dimensional manifold diffeomorphisms or space-time diffeomorphisms, and that these are interpreted as a gauge group of GR. Okay, so that's the, yeah, okay. And it depends on the specific formulation, which constraints exactly you get. On a standard formulation, what you get is sort of a three-dimensional spatial diffeomorphisms as well as a one-dimensional somewhat temporal diffeomorphism, but sometimes you actually get more families of constraints. Okay, good. Anyway, now the received interpretation of the Hamiltonian, in any Hamiltonian theory really, is that it is that which generates the dynamics of the dynamical system described by the Hamiltonian formalism, of course. And if Dirac observables have weakly vanishing Poisson brackets with the Hamiltonian, which they do if the Hamiltonian is, or have to, if the Hamiltonian is a constraint, then they seem to have to be constants of the motion. That is, they can't change over time. So if these are the genuinely physical magnitudes and they can't possibly change over time, that means that fundamentally, genuinely in the physics, there couldn't possibly be any time, even in the very minimal sense that the physical quantities can have different values at different times. And maybe there's another side. Those of you who are philosophers know, of course, there's different ways of thinking about change. There's the A theorists and the B theorists. The A theorists somehow are more demanding because they think it's not enough to have different values for some variable or some property at different times. There has to be some additional sort of oomph that, because spatial variation is, of course, in the same way. If you have a poker, it may be hot on one end and cold on the other end if it's lying in the fire, right? That's a case of spatial variation, and the change you just characterized as temporal variation, essentially completely in analogy to that spatial variation, but A theorists will claim that is only necessary but not sufficient for there to be real change. So let's forget about the A theorists. They're way too demanding. The problem here is somewhat more severe, that even as far as the B theorists are concerned, there couldn't really be change. Okay, and this is the sense in which people have said the dynamics gets frozen and Parmenides is vindicated. Any change that you see is in a sense only just gauge. It's not a physical fact, it's a representational redundancy. It's something that arises from the particular way in which you represent the physical system. Okay, good. Now the question is, back to Parmenides, how can you explain, if the world is fundamentally unchanging like that, how could you possibly account for the sort of change that we see? And not just, in physics labs, in every possible context almost. That's the big challenge now. And now let me go over a very few reactions. I'm not going to spend much time on the reactions in the physics, except that I really want to press together with Ehrman, even though in a way I think he even underestimated how deep the problem is. How can you get, as a physicalist, as a materialist, as not as somebody who's an idealist or a dualist or all sorts of crazy philosophical positions, no. So as somebody who wants to stay close to the physics and explain in terms of basic physics and the material constitution of the world that we can have change and an experience as of change when the fundamental is not changing at all. It seems as if that couldn't possibly supervene on a fundamentally non-changing reality. So it is a deep problem. Now, so look, whenever you have a paradox in philosophy or anywhere, there's different ways in which you can deal with it, right? You can either reject the conclusion and say, something in your reasoning has gone wrong. One of your assumptions, one of your premises, I reject. Or maybe the inference you drew from that premises is somehow invalid. That's one way to reject the paradox. Alternatively, you can embrace or accept at least the paradoxical conclusion. But if you do, then you have to dispel that impression of paradox, right? You have to tell us why it should be okay for us to live with that paradox. Translated to this situation here, that means either you have to accept that fundamentally we live in a changeless world, in which case you accept the explanatory depth of explaining how we can perceive change and how, all other non-fundamental physics is very much dealing in dynamical evolution and change, of course, and so on and so forth. So you accept that as your debt, or else, if you don't, you have to tell us what went wrong in the argument I just sketched. So either you have to point us to some assumption that's unacceptable, or you have to show how we made an invalid move somewhere. Now in the physics literature, now as a matter of fact, these sound very different, but as Bianca has shown, I think in her talk, is that maybe at the end of the day, a lot of what physicists try to do, even though initially they may seem to be completely disagreeing about their way of solving the problem, may actually come to something that's similar, even though the physics, the basic physics may differ, of course, but people like Kucharz or Rovelli all of a sudden perhaps are not saying completely different things, even though, of course, the details in which they solve the problem differ quite a bit. Anyway, it's important to notice that I think, and this is what should get philosophers interested, is that either way there really are formidable challenges that must be faced. Okay. Yeah. So, yeah, there are people who resist the conclusion. That's not so easy as you might think. I'm not going to say more about that. Those who accept essentially that there's the sense in which the fundamental physics is changeless, they face two tasks. One is, I mean, forget about philosophy of mind for a moment and how you can explain our perceptions and experiences and things like that. But just the basic physics, how can we do physics as we normally do it in a fundamentally changeless world? In a way where the Schrödinger equation degenerates, and now I'm talking about quantum mechanics, I guess, into the Wheeler-DeWitt equation, where the right-hand side, where in the Schrödinger equation you have a nice partial derivative with respect to time, here you have zero. How can you do quantum mechanics in a universe like that? How can you do all the usual physics in a universe like that? You have to tell us, you have to give us a theory. And that turns out to be, and this is of course what Bianca and other physicists are trying to do. And this turns out to be really hard. Okay. And secondly, and this is more the philosophy of mind part in a way, you have to explain the phenomenology of temporality. Perhaps if you've solved the first problem, you've solved the main part of solving the second aspect of it. And this is what Ehrman says quite rightly, even though he sort of dismisses it then later, and that's the sense in which I think he sort of even underestimates the depth of the problem here. He says, look, insofar as a physical explanation of the phenomenology must be couched in terms of genuine observables, ultimately of fundamental physical goings-on, the sought-after explanation cannot be purely physical. Now he goes on to, he hastens to add that this does not entail idealism or dualism about properties. And that's true, I agree with him that there's no entailment of those positions, sort of automatic inference to those positions, but nevertheless, the physicalist seems to be in a big, out for a big challenge here. If fundamentally there's nothing that changes, how can you possibly in physical terms explicate that you can have experiences as of temporality without adding in mental things or becoming an idealist. Anyway, let's look at philosophy, and maybe that's the one part which might be new to the physicists who work in canonical quantum gravity. Now, one thing that needs to be said, apart from the Ehrman and Bellot and Jeremy, who have pointed out the problem, there's some reactions, but not many, and I think there should be more. Philosophers should engage more with what's going on here. Here's two people who in philosophy have reacted in different ways to the problem. One of them is Richard Healy at the University of Arizona, and he says, look, about 10 years ago, when there was a sort of a spike of interest in philosophy of physics, he said there can be B-series change, and that means, again, just having different properties at different times, no more than that. Everything else we'll deal with later if we need it. But there can be B-series change in the standard formulation of GR, and he then tries to explain how change can emerge from a fundamental reality which he agrees doesn't change. So he says, look, okay, in this picture, fundamental reality doesn't change, so how can we get an explanation of how we get the change? So in that sense, he is in the camp who accepts the conclusion of the argument, but he says, look, what we have to realize is that now Dirac observables, as central as they may be, are not quite everything there is to the physics in a Hamiltonian formulation. And change can be obtained again or regained if we characterize it properly with respect to a frame of reference. Because after all, we're not disembodied, godlike observers looking directly at the timeless, fundamentally non-changing totality of existence or something like that. No, we are embedded observers, very much part of the world which we inhabit, and so therefore have a particular perspective on that fundamental reality. Now, change, he agrees, can't be captured by the fundamental properties itself. So in a way, if you're God, yes, you are faced with a changeless world. But he tries to then show how if you introduce now frame-dependent observers into the picture, you can regain change. And in a way, there's a lot of parallels, I think, to Rovelli's program, which have been noted by Dean Rickles as well, but it seems not by Richard Healy. It's kind of surprising in a way, I guess, or at least not in the original papers. Anyway, the idea, of course, in Rovelli is that you construct gauge invariant observables somehow from correlations between partial and gauge dependent observables, and that, in a sense, so that you can get objective change if you do that in the right way. Anyway, okay, I mean, it's another question how these relate. Here's another reaction, clearly much more negative than that of Healy. It's by Tim Maudlin. And Tim Maudlin, in that paper I cited already, complained pretty much about every step of the argument that Ehrman and others have produced here. He says these observables, in this case actually not quite the Dirac observables, but for our purposes it doesn't make much of a difference, they lack meaningful contact to what is in fact observable. That's the first thing to note. And that is true. It's the connection between what is called observables in canonical quantum gravity and what in fact is observable is somewhat non-trivial, of course. So that is a fair complaint, but to think that you've thereby brushed aside the problem, of course, would be altogether too quick. And he's concerned mostly with the indeterminism that arises, in the sense that not necessarily the changelessness, but the indeterminism that arises if you have gauge freedom, because that means a complete specification of the variables at one moment in time will not settle the future evolution uniquely, because you have these arbitrary functions of time that enter the solutions. So you have a form of indeterminism. But he says, this indeterminism is not physically salient. He calls it, these are quotes, faux, completely phony, and he thinks it's easily be dealt with in 3 steps or in 3 ways. First of all, he says, well, just ignore it. It's an artifact of the representation. Don't take it seriously. I think, to use another French expression, that is altogether too facile, I think. It doesn't work if you take canonical quantum gravity seriously in any way. And you know what? If canonical quantum gravity is vindicated in that it succeeds to give us not just a consistent quantum theory of gravity, but a true theory of quantum gravity, right? What do you do then? You look like those people who objected to Einstein because it had weird consequences for space and time. It just said this is obviously false and phony or whatever. And those people who complain about quantum mechanics and the weird superpositions and entanglements that you get, well, those people have been caught on the wrong side of history, it turns out. And just brushing it aside like that, of course you run that risk, right? If this program really pans out, well, you know, you can't evade it just by ignoring it. Now, it may not. So it comes down to whether canonical quantum gravity should be taken seriously as a physical program. And if it isn't, then maybe that's justified. But I think this is a long discussion, whether it should be taken seriously and to what extent. And he doesn't engage in it. Okay, so my suggestion is let the foundational chips, as it were, fall where they may, and then deal with it, not just ignore it. Okay. He has another suggestion, and that comes much closer to what physicists in the canonical quantum gravity program actually do. Of course, he says you can fix a gauge, you can remove indeterminism like that, and that's true. It may actually work, as we have seen. In some physically relevant cases. This is what physicists often in practice do, of course, so it's not quite as facile as the first one. The problem is all quantifiable properties will then be depend on the gauge you choose, of course, and hence on the particular way you choose to represent these quantities. So it's questionable whether these really express the genuine physical content of the theory. And what you would need to argue for that is to justify the gauge as somewhat physically privileged. Because maybe really there is a dust or an ether or something like that. Or maybe, you know, from properties, average properties of the matter, you can somehow come up with a physically justifiable way to fix a gauge, or some such way. But you would have to do it. Okay, anyway, there's a third possibility, which is the quotienting out of the indeterminism. That is, cut out all the mathematical surplus structures such that all previously mathematically distinct but physically identical states or solutions get represented by states, in that case, by exactly one point in the now reduced phase space. So that you re-articulate the theory to get to the true physical degrees of freedom. And of course there are methods of doing that in physics as well. This is what physicists do sometimes. Yes?
Can I?
Sure.
Isn't this exactly what leads to the no-time picture
yes,
of the canonical?
Yes. I don't know, do you have my slides in front of you?
No, that's why I'm checking them.
Okay.
So I don't
it is.
Solution.
Yes.
This is exactly what
Yes. Then wait, yes.
The problem in the first place.
So yes, that's right. So in a way it solves the problem with indeterminism. Because you now have only the true physical degrees of freedom.
First he raises the problem that there is an indeterminism. And then he says you gauge away so you solve the indeterminism. Okay.
Yes, but now you have the problem of time. Yes.
There was no problem with
Yes. I'm not disagreeing with you at all. This is what Maudlin says. So that would, of course, free the theory from gauge, and he thinks this is the only principled and acceptable way of dealing with the. In a way, not he thinks. It's the principled way of dealing with indeterminism. But he complains immediately that this is, and these are quotes, leads to the rather silly and crazy and metaphysically monstrous conclusion that there can't be change.
Isn't it suspicious when somebody resorts to name calling?
No, not necessarily. We like to do that in philosophy. So
I mean, because he does have arguments.
So,
he does have arguments that he gives in the. He does say those things. It's rather silly and crazy, but he does give arguments.
Which makes me suspicious about the arguments.
Yes, but the problem is, in a way, what he does is, this is restating the problem. It's not solving it, and so that's not solving the problem here. Anyway, sorry.
Yeah, this is something I was wondering about earlier also. I don't understand this notion of reduced phase space because your gauge transformations are velocity dependent, and a lot of people I'll show you later.
Look, I don't think he is, or I am, saying that this will lead to the solution of the problem. It may, at least in some ways of thinking about what the problem is, in some physical situations. But anyway, okay, good. So
this was sort of in response to what Daniela was saying. I mean, the indeterminism he's referring here kind of goes back to an earlier sort of philosophical literature, the whole argument.
It does, absolutely.
That the diffeomorphism symmetry leads to a kind of indeterminism about what's going to.
Yes.
So the setup is sort of what he's repeating from Ehrman in a way.
That's right.
It's quite clear in there.
Sorry, yes, of course. So that problem is, just to remind you, that the diffeomorphism invariance in GR means that you could have all the fields, all the physical fields completely specified outside of, say, a compact region of space-time, or maybe to the future of some space-like hypersurface or something like that. And all of that, together with the dynamical equations, the Einstein field equations, would not uniquely determine the fields inside that compact region or to the future of that hypersurface. It would only do so up to diffeomorphisms. So in that sense, you have indeterminism. If you think of that which is below your space-like hypersurface as the past, plus the present perhaps, it wouldn't determine uniquely the future in the sense of giving you the field values.
What Tim's saying is that's a phony indeterminism.
Yes, that's right.
That's a phony indeterminism because these are gauge equivalent ways of representing the same. The one unique physics. Now, if you had a real indeterminism, a real indeterminism, like for example some stochastic effects, all this picture will change dramatically.
Oh yes. Yeah. So
a spontaneous continuous localization.
Yeah. Okay, good. Yeah, so anyway, look, I'm not taking a stand here on one side or the other, and I'm not telling you how to solve the problem, neither the physicists nor the philosophers, but what I'm urging is that this is a very serious and interesting problem, and there's really no reason why the philosophers shouldn't get interested in that. Okay. Good, yeah. Anyway, so that's the first part. Now, how much time do I have for the second part? Not much, I realize.
So we have about 15 more minutes.
Okay. So, as you all know, there is this other problem in many approaches actually to quantum gravity, not just in canonical approaches, that the problem is that there's a sense in which space-time, as we know and love it from general relativity, will disappear as being part of the fundamental picture of what the world looks like. The fundamental structures will look very different from relativistic spacetimes. How they look exactly will depend, of course, very much on the particular approach, but they all disappear. So we all talked about that already. And one approach in which there's a sense in which space-time or space disappears as well is loop quantum gravity. And here are my 2 or 3 slides about loop quantum gravity. It's, of course, in that family of canonical quantizations. What you have is you try to find the physical Hilbert space with the physical states that the fundamental system can be in, and try to have algebras of observables defined on that Hilbert space. And you do what you do in a quantum theory. That's the program. Now the problem is there's a lot of not just conceptual but also technical problems in actually following through the entire program, in particular to solving the Hamiltonian constraint equation and to in that way get at the physical Hilbert space. But you get sort of, halfway through the woods, as I think Carlo Rovelli called it some time ago. You get to something which looks like a physical Hilbert space, even though it's only called a kinematical Hilbert space. It's a Hilbert space which has a basis called spin networks. And these spin networks can be interpreted as the fundamental constituents of three-dimensional space in a way we've already seen it in some previous talks. And so these are networks of interwoven loops with representations on the nodes and the edges, and in a geometrical interpretation of what that fundamental structure is, these representations can be thought to discretely value some elementary quantum volume and the area of the adjacency surface between the fundamental volumes. So as I said, that work remains, the theory remains somewhat incomplete, but nevertheless it gives us some idea of what perhaps the fundamental structure looks like. This is, you've seen similar pictures before. So anyway, it's a discrete structure. There's no natural dimensionality to it. There's no metric structure. Even though, of course, these spin networks, which form a basis of that Hilbert space, can be considered as eigenstates of operators that do actually allow a geometric interpretation. Space, of course, in general will therefore be a superposition of these spin networks, because that's a basis, and generically, of course, a state in the Hilbert space is a superposition of these things. So in that sense, generically, you don't have well-defined geometric properties of the fundamental space.
Sorry, what do you mean by natural dimensionality, non-natural dimensionality?
Well, if you have a continuum manifold, there's a straightforward sort of way, standard ways of thinking about the dimensionality of this thing. But, you know, in a discrete structure, you need a somewhat generalized notion of what the dimension is. And I'm not saying that there are no such generalized notions of dimension, but it's not quite so obvious how you measure the dimension of a discrete structure. I mean, mathematicians have thought about this. And there are some ways of doing it. And, you know, it's a similar thing in causal set theory. It's a fundamental discrete structure. What is its dimension? Well, mathematicians like my colleague at UCSD, David Meyer, they have said, well, you know, we should think this fundamental discrete structure has a dimension following the following recipe. And then he gives you a recipe to determine the dimensionality of the discrete structure. And that measure of dimension is justified by the fact that it's supposed to give you something which is very close to the dimension you get when you faithfully embed that discrete structure into relativistic spacetime, something like that.
But isn't this SU2, the presence of the group SU2, going to tell you that the dimensions are this 4? No?
That's motivated. SU2 is motivated by a certain quantization procedure in a given dimension. But the question is, I have the quantum theory now with the dynamics. Can I compute observables that will determine which dimension my states give for space-time? It may not coincide though with the one you started from in the kinematical level and in the classical theory. Another example is in dynamical triangulations, or even asymptotic safety. You start with structures which are 3-dimensional or 4-dimensional. Then you compute geometric observables like the spectral dimension or the Hausdorff dimension of your configurations. And in the continuum limit, the question is whether the number you get is 3 or 4, as you hope, because you use the 4 simplices or 3 simplices. And sometimes it works, sometimes it doesn't. It's a question whether the theory predicts
if the question that you're saying is if the dimensionality of the thing that you end up with coincides with this
kinematical one,
it's connected somehow. This SU2 is going to tell you that you should get 3 dimensions.
Even the fact that you start by building space-time with 4 simplices doesn't ensure that
you will end up
with 4-dimensional spaces.
Yes, and that's a generic problem in I think, quantum theories of gravity where you have discrete fundamental structures. Now, I'm emphatically not saying that there's, you know, this is a problem we can't get around or something. It's just, you know, not so straightforwardly obvious what the dimensionality of these fundamental structures is and how we should think about that. So in that sense, they don't have a natural dimensionality or a sort of automatically guaranteed dimensionality. Okay, and then there's a problem of locality. the locality structures, as it were, may be rather different in the fundamental discrete. Again, this is a generic feature of discrete, of approaches in which the fundamental structure comes out as a discrete structure with adjacency connections between chunks or elementary atoms of space or space-time, in the sense that if you relate that fundamental structure by embedding it somehow, or seeing how it gives rise to, or space-time emerges from that, the locality structure that you have in the emerging space-time, in the sense that perhaps, for instance, you can, space-time distance is not really a good measure for locality, or in some sense it is, in others it isn't, but suppose you have something in which you can introduce, space-time in which you can introduce a cosmological time or something like that, where you have a way of foliating this thing, and then you can introduce spatial distances. That gives you the notion of spatial closeness and vicinity, and now it can turn out, and generically it will turn out, that these fundamental structures have adjacency structures. That's the locality built in fundamentally, the adjacency structures, right? That maps sometimes elements into the space-time that are not close by natural locality or closeness measures in the relativistic space-times. Now these will be suppressed. Why? Well, because if they're not, you didn't do the embedding faithfully. The emerging structure would have to look differently. But nevertheless, they're there. So in that sense, you have funny quantum fluctuations and quantum connections of the spin network or spin foam or causal set that's fundamentally there, which at sufficiently large scales, low energies, and so on and so forth, are smoothed out and are not detectable, but are going to be play a much more important role, of course, in the early universe, for instance, where these things might become quite generic. Anyway, okay,
If they do that, they would break Lorentz invariance generically, right? Because whatever you think is very far away, in some other frame will look very close.
Yes, it's not a simple question. In causal set theory, for instance, there's a sense in which the demand that relativistic space, or causal sets should be faithfully embedded into Lorentz invariant relativistic spacetimes, leads to some funny non-locality exactly because of that mechanism. I don't know, that doesn't answer your question.
No, but just, yes.
Yeah.
Something to keep in mind.
Yes, no, absolutely. Okay, good. So, anyway, the bigger point here is that there's not just a problem of time, as you all probably, or many of you have known coming into this session. In a way, there's also a problem of space, or space-time, in the sense that what we would naturally associate with space, or spatial property, or spatial structure, is not going to be generally available at the fundamental level in loop quantum gravity and in many other approaches to quantum gravity. So in that sense, we have a problem of space as well. Whatever the essential properties of space are, most of them or all of them are not going to be present fundamentally, or not. You have to do some work to show how you get those. And it's the same thing for time. Whatever time is, it's going to look extremely different fundamentally if it's there at all. And that's the problem, what I would like to call the problem of space. Okay. Okay. There's the question of whether space-timeless theories can be even empirically coherent. And this is a question Nick and I have answered in that paper. So read that.
Coherence in what sense?
Sorry?
What's coherence?
Oh, the idea is that if you think that any empirical justification whatsoever for any theory in empirical sciences has to do ultimately, or has to be justified ultimately by the observation of something in space at some point in time, some pointer pointing to this thing, or some reading being this, or whatever it is, something like that. How could you possibly have observations like that in a universe where you don't have space-time? So it seems as if the theory were true, saying that there's no space-time, it would thereby undermine the empirical justification, any empirical reasons we might have for believing it to be true. In that sense, the worry is that it would be empirically incoherent. Nick and I have argued convincingly, I think, that this is not really a problem as long as you can show that space-time re-emerges from that fundamental structure. Then thereby that problem goes away. Now, there's another reason why you may want to show that, that space-time re-emerges from the fundamental structure, and it's because in a context of justification of a theory, as opposed to a context of, so in a way, quantization can be thought of as the context of discovery. You're in the business of discovering the quantum theory of gravity, right? So you apply a way of formulating that theory. But now you have to justify it. Well, how do you justify it? Part of that justification is going to be, as Sam mentioned yesterday, you have to show that this fundamental thing, approximately in the sort of circumstances in which GR is valid, you get relativistic space-times back. So that's part of the justification for any theory of quantum gravity. And I know that my chair is getting impatient here, so I skip a lot of fun stuff. Trading on work Jeremy has done with Chris Isham some time ago when they thought about how time can re-emerge in the canonical context. I think their methods and their notions of approximating procedure and limiting procedure can be applied quite generally to also the problem of the emergence of space-time, as Daniele has shown yesterday. And I was going to argue in this part that this is generally the case. So you have these, and I was going to show that in the case of weave states here and geometric operators. But this is why you have the slides available on the website, so you can all read those and you can read the paper that goes with it. So I come to the conclusion now, where I would like to re-emphasize classical space and time seem to disappear in canonical quantum gravity, or in some sense in any way. And I didn't really show how they might re-emerge. I skipped that part, I guess. Okay. Now, another lesson that was going to be part of the second part here was that, at least on one promising way of thinking about how you regain space-time, which follows Carlo Rovelli in some sense, you get back the measurement problem of quantum mechanics in some version. So don't think that you can evade that problem by going gravity. That's not obviously going to solve that problem. It may, because gravity may give you some mechanisms, for instance, for collapse or some such thing, in which case perhaps that's going to solve it. Anyway, so let me end here. Thank you very much for your patience.
Let me take one from the back there.
Yeah. I have just I wanted to go back to the issue of time in quantum gravity, and I have a proposal for a way to quote Carlo Rovelli, because in this talk it was quoted like time doesn't exist. But I would propose to replace this quote with time doesn't exist, comma, only change exists. This is what Carlo Rovelli says. I mean, the fact that you take away a unique variable identified as time and you replace it with many times, a plurality of times, and this gives ontological meaning only to events, only to interactions without change. So only change exists in this picture.
Right. But not fundamentally, really.
Oh, yes. Why not?
Bianca, you have something?
I
Yeah, maybe I have a related remark, and that is if you put it as a problem of change, then isn't it more the idea that of Laplace and Descartes, once you have a state, the future is determined completely? I mean, I don't see that so much as a problem coming up only in GR, because you can reformulate like in the same way, and then it's just you have given a state.
Well, but generally what you would expect, even in a deterministic theory, in which given the complete state at one time and the dynamical equations, the laws that tell you, how you get to the state at all other times, even if that's deterministic, you can have change. Of course, generally you will have change, because that state will be a different state. The pendulum is over here, not over there, or whatever it is.
But if you go to the parameterized formulation of mechanics, you actually, kind of identify all these states.
Oh, right, yes. Once you make, in all those cases where you make this additional step, yes, then you have the problem of change, yes.
Then you have the same problem.
Yes,
so
absolutely.
It's more, what do you call a state? So do you call states different, appearing at different times, or do you add time and then basically all these states appearing at different times are basically the same states, that what happens in VR in some sense. So then, so then the problem of change is, okay, we are in a given state. It's more like once you determine the state, it's not changing. I mean, I'm not claiming that. It seems that if you formulate the problem as a problem of change, then it seems to go back even,
right, but
to the problem of determinism.
If you set up the problem as I did, then I think it is more appropriately called a problem of change, because what you get is that fundamentally all the basic physical quantities, whatever they are, cannot change over time, so there can't be change. But in a way you could still have time. Perhaps. It doesn't say that time couldn't possibly be there. So it says that there's no change. Now, so you propose that we should think in a Rebellion picture anyway, to sort of flip this around and say, no, time's not there. That's what's been established, yet change is there fundamentally.
So what is change? What is the difference between two states? Is the difference between what?
It's variety, isn't it?
It's
zero time period.
well, that's one way you can have no change, or you can look at whatever So you have your system, which is characterized by its state or by the properties it has, the physically relevant properties, and
if the state should characterize my system, no matter how I slice space-time, then of course there is no difference in state.
Right.
By your requirement, of course.
That's right.
So what's change? What do you compare with what to realize, to see if they are different? Either you slice it and you compare two things into slices, and then you have it, or if you say all these things are the same.
You can say, in response to that, you can say, well, that's a little bit too quick, because of course, while it's true that you can slice your relativistic space-time in all sorts of ways, and there's no privileged way of doing that, on whichever way you slice it, you will find change. The states defined generically, defined on these slices will change, will be different on different slices, however you slice it, even though there's no way, you know what I'm saying?
So you're going to say that the same space-time corresponds to many states. It's the same space-time which is the object of your quantum theory, and you want to say they are different states.
Look, if you want to talk about change in the context of four-dimensional relativistic space-times, you have to come up somehow with a notion of instantaneous states at different times or something like that. And that, of course, is, for all the reasons we know and all the lessons we've learned, is a problematic thing to do. But the thing is, however you do it, and there's no privileged one way of doing it, but however you do it generically, you will get different states and these different slices.
I want to take one more question from Nick Tay over here.
Okay.
So as I understand Ravelli as this on the same topic, in this latest paper, Why Gauge, at least part of how he thinks about change is the relationship between two gauge-dependent observables, right? What you earlier called partial observables. And changes, well, the change of a gauge-dependent observable with respect to another gauge-dependent observable. All that could be true while there's no change in gauge invariant observables.
Yes, that's right. Yeah, absolutely.
I mean, is that consistent with what you've been saying? Is that
I hope. I hope. Yeah.
So in that sense, you agree
So
it's changed?
look, the way I think about this is that if you just look at the gauge invariant quantities, there's the standard way of thinking about the problem, setting it up, that leads to the conclusion that the gauge invariant properties can't change. This is the theory of observables. So in that sense, fundamentally, there's no change. And now Ravelli has this approach where he looks at relations between partial observables that change and tries to reintroduce, I guess, fundamentally thereby reintroduce change.
So I guess my question for you is, do you think that's a sufficient definition of change for our purposes?
Why not? Yes, it's at least something. It's not going to satisfy everybody, but it's better than be stuck with the conclusion that there's no fundamental change. Yes, absolutely. So it's progress in that sense. Whether it's going to satisfy everybody.
On that relatively optimistic and definitive note, shall we take, let's say, 10 minutes? We'll start again at about 4:00.